Okay, so we're dealing with quadratic congruences, and a quick review. And last time we introduced this object called the Legendre symbol. Okay, the Legendre symbol is a kind of piece of notation which, for one thing, it saves us having to laboriously repeat the phrase, this is a quadratic residue modulo that all the time. So it gives us this notation n, which is the Legendre symbol np. Very often we'll just read it as Legendre symbol np. And we write it's +1 to mean that the n is a quadratic residue modulo p, -1 to mean it's not. Okay, so if it's +1, it means n has a square root. There's something else which squares to n. If it's -1, in the other half of the elements, those that don't have a square root, which aren't the square of anything. Okay. And there's this general project that we'd like to be able to evaluate this for given n and given p. Evaluate it efficiently and in a kind of nice way that shows good understanding of the underlying structure. And for one thing, being able to evaluate these, this is what allows you to determine whether or not a given quadratic congruence will have solutions or not. Now, last time we looked at Euler's criterion, which is one way of evaluating it. So if somebody throws you an n and a p, how do you work out if it's +1 or -1? Well, you work out if it's +1 or -1 by working out n to a certain power, n to the power p -1 over 2. Okay, so this is the results we proved last time. Okay. Remember the Euler symbol np is ±1, and when we started considering n to the power p -1 over 2, we found that had to be ±1 because that's the square root. You see, that thing is the square root of n to the power p -1, and Fermat's little theorem told us that that was always congruent to 1 modulo. So you take your n and you work out p -1 over 2, that power, and you consider that modulo p. And this will give you +1 or -1 modulo p, and that will be exactly the Legendre symbol. So that will take that in one sense, that will tell you whether or not n is a quadratic residue modulo p. Okay, so we proved that last time. So, okay, if you're happy enough with that as an answer of how to evaluate it, you can stop here. But some issues to do with this. I mean, as n and p get very large, working out this exponent becomes more awkward. Also, it's not immediately obvious looking at this power what value it has. Given a particular n and a particular p, there's no way to kind of understand whether it is + or -1 given structure or information about the n and the p. You kind of just have to go and evaluate. So we'll be looking for more, kind of get as much meaning out of it as we can. Okay? Okay, so we're going to do a few things with this today. The first couple of which are consequences of this result, Euler's criterion. Or any questions about it first? Any questions about this result or this criterion? So we proved it last time. Now we're going to do some work with it. Okay. So the first result is well, there's these two theorems, or maybe theorems is too grand a word. Maybe they should be lemmas instead. But first is theorem 8.5. Coming up okay. Theorem 8.5, and this gives a very nice description of the status of -1. Okay. Now, +1, of course, is clearly a quadratic residue. +1 is the square of 1 and -1. So 1 + 1 is always a quadratic residue. -1 is sometimes a quadratic residue, and sometimes not. Okay, the initial examples we looked modulo 7, 11, 13, 17. We looked at all those. Sometimes we found that -1, or another way of thinking of it is p -1, of course. Remember, -1 is congruent to p minus 1 modulo p. So the last congruence class before you get to p. What's the status of this? Is this a quadratic residue or not? Okay. Well, okay, so you can see the statement of the theorem is about, well, it is or it is not based on what the value of p modulo 4 is. And we can see this proof is just a kind of 1 or 2 line result, just applying Euler's criteria. So applying Euler's criterion, this will be -1 to the power of p minus 1 over 2, congruent to this. This is by Euler's criteria. And the general result is that the Legendre symbol is congruent to n to the power of p minus 1 over 2. But because our n here is -1, we can write that it's actually equal to. It's actually going to be equal to -1 to the power of p minus 1 over 2. Okay. The Legendre symbol is something which is +1 or -1 by definition, and a power of -1 is, of course, +1 or -1. Now, what value is this here on the right-hand side that I'm looking at? What's the value here on the right-hand side? It's -1 to the p minus 1 over 2. What's that equal to?
1.
Or, yeah, well, 1 or
-1.
or -1. It's a power of -1. It's +1 or -1. When is it +1?
When the index is 2, even.
Exactly, even. When this power up here is even, we get a +1. And when is it -1?
When it's odd.
When it's odd, yeah. So we completely understand how that's going to come out as +1 or -1. It's going to be +1 when p minus 1 over 2 is even, -1 when p minus 1 over 2 is odd. +1 when p minus 1 over 2 is even, -1 when p minus 1 over 2 is odd. I mean, you could leave it at that. You could leave that to be your conclusion. If you're given a p, you can easily work out p minus 1 over 2. You can easily tell whether it's even or odd. There you've got it. Something describing completely the status of -1 modulo p, whether or not it's quadratic residue. The only thing is, rather than leave these conditions left there like that, just like to express them in maybe a little bit more of a convenient way, maybe a little bit more of an appropriate way, just in language that's kind of fits in with everything. And you know, we're talking about congruences, so we'd like some kind of modular type version of those statements. Okay. So remember, p is an odd number, so you've got all the odd numbers. P is in addition to prime numbers, so we're only worried about prime numbers. But when is the number p minus 1 over 2 even? So these are odd numbers. So this is an example, 3. 3 minus 1 over 2 is odd. This is an odd one. 7 minus 1 over 2 is odd again. 7 minus 1 over 2 is 3. So that's another odd one. 11, if p was 11, that would give rise to p minus 1 over 2 being odd again. So these are all odd ones. They're all odd numbers, right? But I'm talking about the p minus 1 over 2 being odd. And so on. These other ones would be even. So 5, when you go 5 minus 1 over 2, 4 over 2 is 2, so that's an even one. Not well, okay, 9 isn't prime, of course, but just as a number, 9 minus 1 over 2 is 4, so that would be another even one. 13 is prime, 13 minus 1 is 12, over 2 is 6, again, that's an even. 15 will give you an odd, 17 will give you even, gives you 8, and 19 will give you odd. So you can see very clearly what's happening. It's just alternating, okay? How to describe that alternation in a precise modular arithmetic way? Well, it's to do with the status of the number modulo 4. Okay? 3 is minus 1 modulo 4. 7 is minus 1 modulo. 11 is minus 1 modulo. The ones that give you an odd number are all 1 less than a multiple of 4. They're all minus 1 modulo 4. The ones that give you an even answer are all 1 greater than a multiple of 4. So they're all congruent to plus 1 modulo 4. So this condition is exactly equal to plus 1 when p is plus 1 modulo 4, and minus 1 when p is minus 1, or you see, if 3, since p is 1 modulo 4, that means it's 4q plus 1. So p minus 1 over 2 is equal to 2q. It's clearly even. So not just relying on observing that pattern, but actually proving it. If p was 4q plus 3, that implies that p minus 1 over 2 is 2q plus 1. 2q plus 1 is clearly an odd number, isn't it? So when p is 3 mod 4, this exponent is odd. The minus 1 to the power of it is minus 1. The Legendre symbol is minus 1. So minus 1 is not a quadratic residue. And the opposite conclusion when p is congruent to plus 1 modulo 4. Okay. So that's the proof of theorem 8.5. So it gives us a complete description of whether minus 1 is or is not a quadratic residue, is or is not a square. So what's the next, what's the next candidate to try and describe? Well, status of 2. In a number of the examples we've looked at, sometimes we observe 2 to be a quadratic residue, sometimes it wasn't. And we didn't really see any, we saw some examples where it was, some examples where it wasn't. There was nothing very obvious about the examples where it was, where it wasn't. So we couldn't really see any clear idea for what the result should be. If we did a bit more numerical investigation, if we tested like the first 100 primes and found out when 2 was a quadratic residue, when it wasn't, just by trial and error, we got a fair bit of data, then we might start to see the result emerge. But we'll take an alternative approach now. We'll just we'll apply Euler's criterion and force it out of that. Okay. So what we desire now is a similar result, but except for 2. So what's the status of 2? This is theorem 8.6. And there's a full proof of it in the notes. But I'll just sketch through the main ideas in it, the main parts in it here on the board. But let's write the result down first. So it's plus 1 or minus 1. And again, it's based on a modular arithmetic or a congruence description of p. But this time it's based on p modulo 8. And p being an odd prime, modulo 8, there's just the possibilities of 1, 3, 5, and 7. You can't have 2, 4, or 6 mod 8 because those will be even numbers. They're multiple of 8 plus something even. So the only possibilities for a prime modulo 8 are 1, 3, 5, and 7. And the way the classification works is if it's plus or minus 1, modulo 8, it is a quadratic residue, and if it's plus or minus 3, mod 8, then it is not. So plus or minus 1, alternatively, you can describe that's 1 or 7, and plus or minus 3, that's 3 or 5. But that's the structure of the result. The status of p modulo 8 tells you exactly the status of whether 2 is a quadratic residue. Okay? What the Legendre symbol 2p is. Okay. Now the proof comes from Euler's criteria. Okay. So this will come from Euler's theorem, Euler's criterion. Namely, that the status of 2 modulo p is congruent to 2 to the power of p minus 1 over 2 modulo p. Now, so what we're seeking to do is to evaluate 2 to the power of p minus 1 over 2 modulo p. But we're not dealing with a specific p. We want to talk about all p. We want to try and somehow do some work to evaluate it in general, and then see how the answer falls out as plus or minus 1, depending on the status of p modulo 8. Okay. And you'll see the proof here outlined. It's a really nice calculation. It's not amazing. To be honest, it's not. I don't have a very good or clear motivation in my mind for explaining why the proof is the way it is. But it's some nice kind of manipulation of integers modulo p. Okay. So what we're going to do is we're going to consider all the even congruence classes mod p. That is the congruence class of 2, 4, 6, 8, and so on. And p minus 1 will be the last one, won't it? Okay. P is an odd prime, so the last congruence class, p minus 1, that will be an even one. So we're going to consider all these, and we're going to consider their product. So we'll form their product. 2, 4, 6 by 8, 10, etc., all the way up as far as p minus 1. Now, we don't do any modular arithmetic on it at first. At first, we just make the move that, you see, all of these are even, so you can extract out a factor of 2 from all of them. And we'll leave behind 1 by 2, by 3, by 4, by all the way up as far as p minus 1 over 2. So how many 2's did I see? I divided each factor by 2. How many 2's did I take out? Well, I took out p minus 1 over 2. So it's 2 to the power of p minus 1 over 2. And we've also got a nice description for that other factor in the brackets. This is simply p minus 1 over 2 factorial. Isn't it? It's the product of 1 times 2 times 3 times 4, all the way up as far as p minus 1 over 2. Remember, p minus 1 over 2 is a perfectly good integer. P is an odd number, it's a prime number, large odd prime number. P minus 1 is even, so p minus 1 over 2 is indeed an integer. We're not sneaking in fractions into our discussion. Okay, so on the one hand, the product is the product can be written like this. Second way of considering it is going to be slightly trickier, slightly more mysterious. So next, we consider the same product in a modular sense modulo p with alternating positive and negative signs. Okay. That's a kind of vaguish description of what we're going to do. Here's what we're going to do precisely. We're going to start from the end of the list. So p minus 1 So p minus 1 is one of the factors, and we consider that as being congruent to minus 1. P. So that's 1 from the end. Then we take 1 from the beginning, which is 2. And we'll just consider that as 2. And then we'll take the next one from the end. So the next one from the end is p minus 3. Now, p minus 3 is, of course, minus 3. But I'll get my minus sign by cubing 3. And I'll get my positive sign here by squaring 2. I'll keep going in this fashion, alternating from the end and the start of the list, and alternating whether I'm taking the positive or negative of the number. So the next one from the start of the list is 4, which I'll consider just as 4, and I'll get myself a plus sign for that, which I'll consider as being minus 1 to the power 4. Then I'm going p minus 5 from the start, which I'll consider as minus 5, the minus sign coming from minus 1 to the power 5. Now, I'm selecting elements from the end and start of the list, the end and the start, the end and the start. So this is going to end, but it's difficult to say whether it ends with picking the last one from the start of the list or the last one from the end of the list. It depends. It depends on the kind of deeper parity of P. So this is going to end with S being congruent to P minus 1 over 2, certainly. But it's debatable whether that P minus 1 over 2, whether it falls at the end of the initial half or the beginning of the second half. So this will be minus 1 to the power P minus 1 over 2. Okay. So this is where S is either P minus 1 over 2 itself, or P minus 1 over 2. Just I'm not sure. Depends on the status of P, probably modulo 4, whether or not I finish with the last one at the beginning of the list or the beginning one, the initial one from the second half of the list. But we will agree that what I have down here on the left-hand side, is all the even congruence classes. Okay, so I've got the congruence classes of 2, 4, 6, 8, and so on. P minus 5, P minus 3, P minus 1. P minus 1 is the last even congruence class modulo. So I have got them all there. I'm going to multiply them together again, which will give me this thing on the left-hand side up here, 2 by 4 by 6 by 8. But it'll also give me a different modular arithmetic description. Okay. Taking the product of all these, by 2 by 4 by 6, all the way up as far as P minus 1. That's multiplying together everything on the left-hand side. It's not an equation now, it's a congruence. These are all congruence statements. Congruence statements. So on the right-hand side, I've got the product of all these. But what have I got here? So I have to multiply all these things here together. So you see, I'll have P minus 1 over 2 factorial. 1 by 2 by 3 by 4 by 5 times P minus 1 over 2 factorial. So the factorial gives me the product of all these first factors. Then I have to multiply together all these minus signs. So multiplying together a load of powers of minus 1 gives me minus 1 Now I'm multiplying together these different powers of -1. So what do I do with the exponents? I don't multiply them together, I have to add them. Yeah. Just using the rules of indices. So this is 1 plus 2 plus 3 plus all the way up to the last exponent, which is p minus 1 over 2. And this is a congruence modulo p. Now it's nice that I got the factorial again. So I got the factorial before. So I'll be able to relate the two together nicely. Now, okay, I want to simplify this. So instead of this long sum in the exponent position, I want to get a nicer description of that. But that's just, it's kind of your basic arithmetic sequence. Just adding up 1 plus 2 plus 3, adding up the first p minus 1 over 2 integers. Well, remember, if you want to add up 1 plus 2 plus 3 all the way up as far as k, remember the rule, it's k plus 1. You add them up, you pair them, beginning and end, k plus 1, and you k over 2 times that. That's the formula for adding up this basic arithmetic sequence. So I just want to apply that here in the case where k is p minus 1 over 2. So this becomes p minus 1, minus 1. So k over 2, so it's going to be p minus 1 over 4 multiplied by k plus 1. So it'll be p plus 1 over 2. And we may get even more worried here. Is this an integer I've written down? It looks like two fractions multiplied together. Well, of course it's an integer because it's just the sum of all these integers. P minus 1 over 2 is definitely an integer. There's a load of integers added together, so it must give an integer in total. P minus 1 over 2 factorial. Just cleaning this up a bit. P minus 1 by p plus 1 is p squared minus 1 all over 8. So sorry, that's I didn't write that very well. I wrote that too big. This is the exponent. Exponent of minus 1. This is like the power. Yeah, I just wrote it a bit too large. It's looking like it's multiplied by that. It's not. It's the exponent of minus 1. So this is modulo b. Now what's going on here? See, I've calculated two things. Both times I multiplied together all the even congruence classes. 2 by 4 by 6 all the way up to p minus 1. Here I did 2 by 4 by 6 all the way up to p minus 1. The first time I got it just very simply by factoring all minus 1 over 2 times this factorial. 2 to the p minus 1 over 2 is good, because by Euler's criterion, that's congruent to the Legendre symbol. That'll give me my plus 1 or minus 1. That links it to the Legendre symbol. The second way of working it out is good. I get the same factorial there, and I get minus 1 to the power of p squared minus 1 over 8. Again, that's just a power of minus 1. It's very easy to analyze when this is plus or minus 1. It just depends on whether this exponent is odd or even again. So equating these two forms of the product, 2 times 4 times all the way up to p minus 1 over p minus 1, equating those two, what I get is 2 the p minus 1 over 2 times the factorial of p minus 1 over 2. I get that this is congruent to factorial of p minus 1 minus 1 to the p squared minus 1 over 8. Now, at this congruent to that, I've got the same factor in each of them, which is this factorial. Can I cancel the factors? I've got two expressions which are congruent, modulo p. I can see a clear common factor. Am I allowed just to cancel out the common factor? If it was an equation, no problem. You just divide both sides by that number. This is an equation. This is a congruence modulo p. So the correct operation to do is to multiply both sides by the inverse of this quantity modulo p. Does it have an inverse modulo p? What's the criterion for having an inverse modulo p? What's the test you have to pass in order to have an inverse modulo p? Modulo n, modulo anything. You have to be co-prime to the modulus in order to have a multiplicative inverse. Yeah. Now p is a prime number, so everything less than it is co-prime to it, because p doesn't have any factors really, apart from itself and 1. And this factorial is certainly made up as a product of numbers less than p. So you've got a bunch of things in this factorial multiplied together. All of them are co-prime to p. So the product is going to be co-prime to p. Okay. All the factors that p minus 1 over 2 factorial it has, it doesn't share any of them with p. P is a prime number. And it certainly doesn't have a factor of p here, because all these numbers are less than p. No p in the product. So yeah, so the conclusion is yes, we are allowed to cancel this from both sides. We can multiply both sides by the multiplicative inverse modulo p of this factorial. Cancel. 2 to the power of p minus 1 over 2 is indeed congruent to minus 1 to the p squared minus 1 over 8. And of course, by Euler's criterion, this is the Legendre symbol. 1 to some power. We'll analyze it now to see whether it's going to spit out a plus 1 or a minus 1. And that plus 1 or minus 1 will be the Legendre symbol, telling us whether it is, whether 2 is a quadratic residue, mod p, mod this p, or not. Now, how do we analyze this to see what value pops out? It's exactly what you said. It's a power of minus 1. So if this exponent is even, it's going to come out as plus 1. If the exponent is odd, it's coming out as minus 1. So the Legendre symbol 2p is plus 1 when p squared minus 1 over 8 is even, and minus 1 when p squared minus 1 over 8 is odd. Now again, just like in the minus 1 example, we'd just like a nicer description of that in terms of some congruence classes. Okay. Now we're dividing by 8 and looking at whether it's even or odd, so it'll probably be congruence classes modulo 8. So if you look at modulo 8, how should we lay this out? So we can draw up a table. What are the possibilities for p mod 8? Well, any prime modulo 8 has to be one of these 4, doesn't it? 1, 3, 5, or 7. You can't have a prime being congruent to 2, 4, or 6 modulo 8, because then p would have a factor of 2. It wouldn't be a prime number. So that's p mod 8. P squared minus 1 mod 8. I have to go a bit deeper. Yeah, we have to look at, to answer this question, we have to, let's just get a little zero. Yeah, no, I won't bother I won't replicate the table. But look, you see at the top of page 67, this is the table I need. So sorry, it's a little bit more complicated. So let's look at this table at the top of page 61. Well, it's the same thing. First of all, we consider P modulo 8. So let's got this. The table in notes. Page 61. This is the table I'm talking about. We want to analyze P squared minus 1 over 8, decide if it's positive or even. Modulo 8, so it's 1, 3, 5, or 7, and it's a certain multiple of 8. Well, when you square it minus 1, you get these expressions out. Just squaring these expressions, subtracting 1. Then you divide it by 8. Yeah, so we need to see the factors of 8 and everything. We divide it by 8 in the eight q squared plus 6q plus 1, etc., etc. There's the form of p squared minus 1 over 8 in each of the 4 different cases. These numbers we can observe and we can tell whether they're odd or even. Because the polynomial type part, the q squared and the q, see all the coefficients there are even. So the bits involving q in total give you even. So the even or odd nature is determined by the final remainder, isn't it? Remainder 0, it's even. Remainders 1 and 3, it's odd. But remainder 6, it's even. Remember, this quantity p squared minus 1 over 8, that's the exponent of the minus 1. So when it's even, you get plus 1. When it's odd, you get minus 1. So this gives us our final conclusion. We see that 2 mod p, the Legendre symbol 2 mod p, plus 1 in the cases where we have 1 or 7. P congruent to 1 or 7 modulo 8, and minus 1 in the other 2 cases, P congruent to 3 or 5. Once again, just like in the minus 1 case, we end up with this nice, succinct description of the status of 2 modulo p. We can say exactly when 2 is going to be a quadratic residue. It's whenever the prime is 1 greater than or 1 less than the multiple of 8. And it's a non-residue whenever it's 3 greater than or 3 less than the multiple of 8. So given any prime number p, very quick test to tell what it is modulo 8, and then you know the status of 2. Now, you could imagine continuing like this, trying to construct proofs, for every single number in here. However, you'd never be finished, of course, because there's an infinite number of integers. And the prime numbers get arbitrarily large, so you would need an infinite set of results about having anything in here, modulo p, applying Euler's criterion to try and decide what the status of the number is. So you could say it's tempting to continue like this. But when would it end? That's the question. Well, it wouldn't end. You'd have an infinite number of results to get through. So we're still looking for something deeper, some kind of deeper understanding. Okay. The rest of the chapter works towards quadratic reciprocity law. Quadratic reciprocity law is this really nice result. See, reciprocity is about things going back and forwards, reciprocal. Me to you and you to me. It's that kind of interchange idea. If P and Q are two primes, this is our first look at quadratic reciprocity. Quadratic reciprocity relates these two Legendre symbols. The one on the left is talking about whether or not P is a quadratic residue modulo Q. Yeah. So whether working with arithmetic modulo Q, whether you can find a square root for P, yes or no, plus 1 or minus 1. This Legendre symbol is the reciprocal idea. Whether working modulo P, you can find a square root for the congruence class represented by the prime Q. Now, if P and Q are two distinct primes, there is no at all simple relationship between the multiplicative system modulo Q and the multiplicative system modulo P. You got two different primes. It splits the integers up into different congruence classes. And there's no reason at all, well, from where we stand now, there's no reason at all to expect there to be any connection between the system of integers modulo Q and the system of integers modulo P. From our current standpoint, from the number theory we've developed so far. However, there is an extremely very easy to state, takes a bit of effort to prove, there's a very easy to state relationship between these two Legendre symbols, between the status of P modulo Q and Q modulo P, about whether or not they are squares, quadratic residues. And these is that these two are equal most of the time. Most of the time, P and Q, either they're quadratic residues modulo one another, or they're not. The Legendre symbol has the same value. It's either +1 for both or -1 for both. That happens most of the time, precisely 3/4 of the time. The one case where it doesn't hold is where it always goes exactly the opposite. So one of them will be a residue modulo the other, and the other won't be modulo the first, or vice versa. But they have opposite states. Now the conditions on when each happens is very easy to state. They have opposite property, opposite status. So if this is +1, this is -1, and vice versa. If QP is -1, then PQ is +1. They have opposite status exactly when both of them are congruent to 3 modulo 4. And they have the same status in all other cases. This is the law of quadratic reciprocity. And it's this law, which we'll talk about next time, but this law will enable us, will give us a very, very efficient way of evaluating our Legendre symbol for any inputs. Okay? Very, very efficient way. I won't go through it now because it'll be a bit too rushed. But this is our first look at the law of quadratic reciprocity, and this occupies the rest of the chapter in proving this. And it seems kind of surprising because at first look, as I said, there's no reason to suspect strong connections between the integers modulo 1 prime compared with the integers modulo a different prime. They're completely different systems, different sizes, different things going on. However, there's this intimate connection between the residue status of the primes modulo each other. 3/4 of the time they have the same status. 1/4 of the time, for picking random primes, they'll have opposite status modulo one another. So this is from when you first see it, it's a surprising result to see this very strong connection between the two systems, where we haven't had any kind of an inkling of any kind of strong connection between the two systems up to now. So this is going to be a powerful result which will help us to evaluate the Legendre symbol for general inputs. Okay. Okay, so thanks for listening. We'll leave it there this afternoon, and I'll see you on Friday again. Expect the coursework to be coming back to you on next Monday, is the schedule we're working to now.